So hi everyone, my name is Jelena Pjesivac-Grbovic. I'm a staff software engineer in big data. I am TL for MapReduce and a part TL for Dataflow service. So today I'm going to talk about Apache PIM, which is our incubating project, and Google Cloud Dataflow. The talk consists of 4 parts, and the first topic is the data that inspire us. It's infinite out-of-order data sets that we try to process and extract the meaning from it. We'll then focus on 4 questions that are at the core of Dataflow programming, PIM and Dataflow programming model. And then we'll focus on Apache PIM followed by Google Cloud Dataflow. So infinite out-of-order data sets. You and your users, everyone generates the data. You care about it, you collect it. You don't think about it as a file, you think about it as elements or records that you have, and you want to understand the meaning from them. You have some data, it can grow big, it can grow much bigger, so you have to structure it in logs or daily logs or things like that. But essentially what you're trying to capture is this infinite data stream that's coming into you. And it arrives at certain times. So this is our system time when we became aware of the data, but it comes from all over the world. So it arrives with unknown delays. So let's assume this data point was generated, this event was generated at 8 p.m. or 8 a.m. Pacific Standard Time, and we got it at approximately the same time. Yay, good internet connection. This one here is like 30 minutes delayed. Maybe they went into a subway, they went into the garage, got lost, got out, didn't arrive, but when they connected soon after, and 30 minutes later, it was on our servers. This one here was at the same time, in real time, but arrived to us hours late. Who could that be? Well, a camper who was enjoying nature, playing your game, or some sensor that got disconnected because of the cross-Atlantic fiber cut. So how do we reason about what we can easily do is compute the things that, as they come to us, right? Like we can compute on that. But what we really care about is understanding what was happening at a given time. Not at the time we became aware of it, but at a time when it happened. So how do we do that? Part of it is how we do that, and part is what we may want to do with it. So one of the type of applications we can do is we may want to filter data. So we want to do element-wise transformation on either all elements that we see or elements that, on certain subset of elements. This solves some of application problems, but not all. So often we want to compute some aggregates. We want to see what happened in a certain amount of time, and how many queries came, what type of queries, what was the most popular query, what was the total money generated or lost in the period of time. And for that, we can do one thing, and that's we can do processing time windows. So we can look at all the data that arrived between 11 and 12 and compute some aggregate information from there. But as I mentioned and implied before, what we would really usually like to do is look at the data that happened between 11 and 12 and compute the aggregates on that data. Okay? So this is trickier than the original problem. So when you try to figure out how to compute on these infinite unbounded streams that come with unknown delays, you have to think about the difference between event time and the processing time. And ideally, event happens and we see it immediately, right? In reality, events happen and then we see them eventually, right? And hopefully the delay is not too big. The skew between this line and the ideal line, we refer to the skew. And the wiggly line is the watermark. The watermark describes the event time progress, right? And in a sense, it's like no timestamp earlier than the watermark will be seen in the future. So we think we've seen all the data that will arrive for this event time window, right? Can you do it perfectly? Sometimes, often not. So it's heuristic based. So what are the it's a heuristic based, so then there are trade-offs, right? So if it's too slow, or you delay it until you're really confident, you're delaying the results that you can produce. If it's too fast, you will have late data, right? Like data that comes for the window that you already emitted the result for. Okay? So with this background, we can look at the questions that we try to answer with the PIM programming model. So we like our users to think about what are they computing when they process their data, where in the event time, when in the processing time, and how do they refine the results. So what are you computing? Those are data transformations. They can be element-wise, like a filtering I mentioned, or they can be aggregating. Common aggregates, count, sum, group by key, they're all aggregates. And you can compose them, right? Like you can make really advanced transformations built on top of these two types of transformations. So in Apache PIM, this is our pseudo Java for brevity. But imagine we had a game, and in the game there were teams, and you wanted to compute the team score. Seems reasonable. So what you will do is you'll read your raw input logs or whatever, event logs. You will parse it and split it into team and a score. So each element has something that you can deduce the team and the score for that data point. And so you'll parse it, that will be your input. And then you'll sum per key. So for each team, you'll generate the sum. Seems straightforward. So how does the computation look like? So again, we have event time and the processing time. And imagine these data points are our team scores. Okay? Again, we have the ideal event time, processing time line, right? This is the ideal watermark, but you cannot reach that. 3 is this, the score 3 happened at like 12:06, and we observed it at 12:07, so it's very close to this ideal timeline, right? This guy here happened at 12:01, but we observed it 7 or 8 minutes later, right? So that one is a little bit more, harder to process, right? So how do we compute the total sum for the team from 12 to 12:09? It's not a trick. We just go up and read all the data and sum it up, and we get 51. Great. So that's the score for the team. So this was like a typical how you would do it in batch, right? Like you had all the data that you needed between 12 and 12:10, and you computed the result on that window. In streaming, if you wanted to compute the result and you waited to see the whole data, you would never produce the result. So you have to have other concepts for that. And the windowing allows you to divide the data stream into event time-based finite chunks. So you can do some aggregations on them. Example of the windows that are supported with the PIM model are fixed. So you want like every 2 minutes, right? Sliding, you want to last 2 minutes. So that moves with the time. And the sessions. Sessions are really important for anything that deals with user activity, for example, because you want to understand what the user did when they interacted with your application, website, tool, whatever, right? So these are the bursts. The sessions capture the bursts of user activity, and the bursts can be very different. So this is a pretty advanced use case for windowing, but it's also a very common use case in Google, and I believe pretty much everyone who has users is trying to do the sessions. So yeah, we need windows to aggregate over unbounded data. So what do we need to change in PIM program to support the windowing, to support the results for every 2 minutes? Well, that computation that was just the scores is input sum of integers. We need to apply windowing on it. And we're applying fixed windows, 2 minutes of width. Okay? So how does it look like when it computes? This is what happens, right? We split the time period in the event time from 2 to 12:08 here. And we ended up with the 4 windows, and we computed scores there. Note that this is same for batch and for streaming, right? The sum in these windows looks the same, right? OK, so here we still had all the data. When we computed 9? what happens is, like, when we wanted to compute the first window, because of the 9, we had to wait until all the data came in. So we have to heuristically decide when we have all the data, as we mentioned. So based on this information, we control when we can produce the output. So in this previous graph, output was produced at the end of like at 12:10, right? But if you have a streaming application, you don't want to wait for all the data to appear, right? Like, and for you to be 100% sure that all the data appeared. So you want to trigger as soon as you think the result is reasonable, right? And in Dataflow, in PIM, we control that using triggers, and their triggers are often relative to Watermark. So you can say, emit result when you think you have all the data, for example. So this is how you do it. In fact, this is default, so you don't have to do it, but this is how you would do it. And this is what happens when you have a perfect watermark. So your watermark advances only once you see the all data. So here, you can see Watermark was waiting until it caught up with 9. That meant that all of these other windows didn't produce the result until we passed this one, right? So this is the perfect watermark. More likely, heuristic watermark would emit something like this. So the results for the first window would appear pretty soon. For the second one, they would also be pretty recent. And then, for all of them except for this one, they would be correct. And then we would discover that we have a late data. So there are 2 problems with this. Well, problems or refinements we can do on this. First one is that to emit any result from the later windows, we have to wait for Watermark to move there, right? The second one is that we may want to figure out what to do with 9, right? So first, let's address the first problem, the waiting on the results, for Watermark to pass. You can emit speculative results. And this is our feature called trigger that has early firing. And you want to emit speculative results for a given time window every minute. Sounds reasonable. And then, for the late data, you can emit a new result whenever you see a late data. Okay? So how does that look like? Well, so this is how the picture changes between perfect and heuristic watermark. So here, the watermark still goes like this, but we got our early results on a minute range, right? A minute is in processing time, right? So that's why they're like stacked. So we have this window was emitting results early, and then when Watermark finished, that was final result. And here, we had the ability to pick up this 9 and produce the final result. One thing to observe is, regardless how we were emitting these results, the final result for this time range remained the same. The total sum is 51, and each window has a correct, the same values, regardless how we splice the event time. So essentially, like some of the control knobs that are interesting are what do we do when the data is late, when data is early, when we want speculative results on this, and we have a number of tuning knobs for this, and they're all application specific. So one of the so imagining that we have this sequence of event elements, 3, then at Watermark we get 5 and 1, and we observe 2 as a late, we can, for example, discard late data. It might be okay for some applications, right? So in that case, we are not accounting for this, but we can discard it. We can accumulate, and we can accumulate and retract. So model allows us to do that. We did not implement it yet. So this is an example of how the retractions would, for example, look like. So when you compute the new value, you can retract, like the previous value is no longer valid. Let's subtract that and add a new value. Okay, so what I hope I showed is that by focusing on the 4 main questions, like what, where, when, and how, one can take this infinite unbounded data that comes with unknown delays and actually do meaningful computations on it and can tune it using these essentially 4 dimensions that we allow you to play with and tune. So we covered everything from classic batch to streaming with retractions and sessions. And they pretty much what the data transformations you apply have not changed through any of these application changes, right? So your core computation was the same for all of these examples. And the results we produced are consistent because they're based on the event time, and event time is source of truth, not the processing time, which depends on the ordering. Okay? So this is about the PIM model. Now about Apache PIM incubating project. So the evolution of the PIM. It all started with GFS, but the MapReduce came after that, and it was really popular too. So MapReduce paper came out of Google in 2004 and sparked pretty much big data industry, right, at that point. So since 2004, within Google, we continued to evolve, to learn new things, build new systems, and we continued to publish. And at the same time, sparked by the original inspiration, I guess open source community started to develop and implement their own systems that were sometimes influenced by Google, sometimes original contributions, and overall developed very healthy and strong ecosystem that allows the pretty much cloud industry to thrive right now, right? So inside Google, we looked at all of our data processing frameworks at some point in 2014, and we fought a little bit harder. We noticed we had lots of batch, lots of streaming solutions, things like that, and we were able to combine the batch and streaming concepts into the same programming model that we called Google Cloud Dataflow. And it was great and fine, and in 2015, we went into GA, and we were all excited and love it. And then we looked at and understood that for this to really catch on, it has to give users more flexibility. And it cannot depend only on our experience. For this to be really useful, it has to rely on experience of other people. And this is a huge group, right? So in February, we decided to contribute the code base for part of Cloud Dataflow, the SDK and this, into Apache PIM incubating project. So what's there? What's the part of it? It's the PIM model. It's the thing that focuses on answering the what, where, when, and how questions. Okay? It's the SDKs for writing PIM pipelines, starting with Java. We are working on Python as well. And the runners for existing distributed processing backends. So this is the part that takes the SDK and make it work with the thing that it can execute it, right? And options for our users right now are Apache Flink, thanks to Data Artisans, Apache Spark, thanks to Cloudera, Google Cloud Dataflow, our fully managed service running on Google Cloud Platform, and the local in-process runner for testing. Okay. So we're actively working on growing PIM community. We're looking for folks to collaborate, and we want to grow it. So we have our meetings, some in Seattle, some here recently, and we are trying to be a good citizens in OSS community. So if you're interested, reach out to me after the talk, and I'll be happy to hook you up with whoever you need to be. So what's our technical vision? So with the PIM, we hope to address needs of 3 users. First one are end users who want to write the pipelines or transform libraries, I/O connectors in the language that they're familiar. They actually want to solve the problems, and they're going to write the PIM job to do it. Okay? So these are these guys. We want to also help SDK writers. So programming model is more than a language in which it's implemented, right? So we are contributing Java and Python, but we had requests for Scala, requests for Go, etc. So we cannot implement all of them. We don't have expertise nor energy. So, but we are making it possible for other folks to come and plug in into the worker harness, this PIM model pipeline construction level, and you just work on this level, and everything else falls into place. And finally, we want to encourage and empower runner writers to get a new set of applications running on top of them. And those examples right now are Apache Spark, Flink, and Cloud Dataflow. Right? Like we already have 3 different, and local test runner. Right? Like we already have different runners that work under this stack. So this brings us to Google Cloud Dataflow. So what is it? It's a fully managed service for running Beam pipelines. It's dynamically provisioned, on-demand resources. We start up VMs for you. We install them. We shut them down very quickly. We are also no tuning required platform. So we have auto-scaling and dynamic workload balancing. And this part was built on top of extensive experience we have with our internal tool at Google. So this is essentially, this part of the service is really taking the best that we have internally and then making it available to external users. The Cloud Dataflow is actually shared stack with our internal flow. So what is dynamic workload balancing? It's an advanced regular mitigation technique that ensures that all tasks finish at the same time. Let's look at a traditional MapReduce job. 2 stages. X-axis is time. This is around 20 minutes. And these are workers. So I don't know, they were like 50, 60. So one horizontal line shows a worker working. Like the green thing means worker is busy. White thing means I'm idling my thumbs, right? So without dynamic worker balancing, we can see that the stragglers in the first stage are essentially costing us almost 50% of time spent in the first stage, right? And the second stage cannot proceed because it has to wait for everything in the map phase to finish. The stragglers are even worse in the second stage, right? Like this is almost 50% of runtime in these few remaining tasks. Stragglers are nothing new. I think every single distributed data processing tool tried to come up with the methods to do it. We tried many, many different things, and this seems to stick. And this is with the dynamic work rebalancing. So what we do here, and you can see this white area, this is the part where we find out that there are idle workers. Hey, someone finished. And then we make other workers split up their work on demand. So it's not the worker stealing. It's slightly different. And rebalance, essentially, how the work is executed. And that shortens the duration of the first stage, and we almost get rid of all the stragglers in the second stage. So the job is finished. The x-axis is the same duration. So we are done pretty much on line where this guy was done. Okay? So it's a pretty powerful technique. So this is with the fixed resources. This is how we fill them up better. Improves utilization and all that jazz. But another thing that it enables is our and we had a pretty cool blog post on no shard left behind. I strongly encourage you, if you think this is interesting, I strongly encourage you to look at it because it covers some technical challenges, why this wasn't easy to get right, and how you ensure that it stays right, because it depends on the user code to implement this for a given source. Okay, so another thing that we do is auto-scaling. So auto-scaling dynamically adjusts to the number of workers, dynamically adjusts number of workers to match the load. So in streaming, because remember, Cloud Dataflow is for both streaming and batch, we have a rate of a game events that spiked. Like the spike is 4x of the stable, right? And this was like, I think, 10,000s a second, so it's not a big job. And then the number of workers was, low, like few workers, and then it jumped up, 10x, and then come down as needed, right? In batch, using the dynamic worker balancing, what we can actually do, well, we estimated that we needed a few workers. It turned out we were wrong, so we kept growing the worker pool, right? And constantly keeping it busy. So like this empty space here is these workers did not exist. Right? So you can end up starting with very small number of workers. If it turns out it's a bad estimate, you can actually adjust for it. And all of this happens automatically. No user interactions needed. So for this one, we had a blog post comparing what we do for auto-scaling versus Spark versus Hadoop. So I think if you type it in Google, it shows up. OK, so the Cloud Dataflow itself is part of the ecosystem. So data processing is only as good as your ability to reach the data that you need to process. So we're fully integrated clearly with the Google Cloud products like storage, BigQuery, Bigtable, Datastore, PubSub. So you can process data in any of these storage solutions. And PubSub is the streaming one, and I think you can write in streaming fashion to pretty much all of them. And we also integrate with external. We have a pretty nice, well, Beam has a pretty nice custom I/O API, and you can implement your own connectors. So right now we have Kafka and HDFS. You can access data there, but there are many in flight. Again, we're part of Google Cloud Platform, so if you're trying to compute things, like you get nice monitoring UI, we are integrated with Cloud Logging, Debugger, Profiler. You can do right-click and see your stack traces. And we have a stack driver integration, so you can do your operations and monitoring in a simple and smooth way, right? So if you're doing the streaming pipeline, you can have alerts when you have a spike in the usage, for example. System will adjust, but you may want to know about it. Okay, but Dataflow is not the panacea. Like the thing we know at Google is if you want to process data, you should use the right processing tool. And the right processing tools in Google Cloud Platform depend on your use case, and they all work well together. So you should be free to use whichever you want, right? So we have BigQuery, which is our fully managed, economical, and fast data warehouse solution. We have yours truly, Dataflow. We have Dataproc, which is the managed Spark and Hadoop service. So you don't have to spend time setting up your Hadoop cluster or your Spark cluster if you have your applications. It's pretty much click away from running one of those. We have Data Lab, which is in beta. It's an interactive, large-scale data analysis and exploration and visualization tool. So it allows you to see what your patterns in your data. PubSub is our asynchronous messaging service, large-scale, at least once, many-to-many. And finally, we have Genomics, whose goal is to empower scientists to organize world's genomics data. More interesting things that are coming from Google Cloud are machine learning. One thing that we do a lot internally is machine learning our data. And we have machine learning platform. This is in alpha. This was announced in February. And this allows you to write the application that harness the power of different machine learning solutions that we have in Google that we're exporting through this. And if you have more specific and narrow problems, we have vision, speech, and translate APIs, which allow you to integrate our expertise in machine learning in these areas into your products that need image analysis, speech translation, and multi-language support. Okay, so to learn more, we are on Twitter, and essentially we have our Beam incubating blog post on Apache, the website. Cloud Dataflow is cloudgoogle.com, Dataflow. And we have Cloud Platform, and we run Beam on Cloud Dataflow on Google Cloud Platform.
We have some time for questions. So I actually had a question related to the beginning of your talk when you talked about the watermark. So one challenge that I find is actually who should generate the watermark? How do you know that you actually have seen all the data? Is it the application? Is it the engine?
So that's an excellent question. So in our case, the watermark is generated by the system. And it relies on our input sources being able to tell us some kind of a timestamp. Now, implementer of the source controls the timestamp they tell us. But we are the ones doing aggregation and figuring out what happens. So with Google Cloud, with PubSub that we have pretty accurate estimates in sync with them. For more custom sources, it will be as good as the information you give us.
Okay, because then the related question is how much state will you keep before? So as the data arrives, you can process it in memory directly. But eventually, if the sources don't generate timestamps for a long time, then you might need to start to spill to disk or something because you're keeping the state so long because you might actually generate a final value.
So we do, we do persist the data, and we are subject to physical laws. But in general, we can handle like a pretty large data sets and accumulate quite a bit of data because we can persist it, and then when the trigger fires, we can extract it and produce the final result. But that's a good observation. If you wanted to have a windows of a year and weren't careful on how you're processing the data, physics might kick in.
Great, thank you. Other questions? All right, then let's thank our speaker and move on to our last speaker.